Good afternoon, everyone. I'm Ziqian Lu from Zhejiang University. So today I'm going to present our work, Attentive Semantic Preservation Network for zero-shot learning. This is joint work with my colleague Yunlong Yu, Zhe-Ming Lu, Feng-Li Shen, and Zhongfei Zhang. The goal of zero-shot learning is to learn a classification model for new classes by using a few labeled classes. As shown in this figure, the images are divided into subclasses such as horses, penguins for training, and unclasses such as bats and dogs for evaluation. So, we should learn a classification model on subclasses and use the model for unclasses. Why zero-shot is must? Because it's impractical to collect or annotate enough data for each class, and there are many challenges in object recognition, lack of larger scale images, lack of images in spatial domain, and many others. In order to explain zero-shot learning more intuitively, we give an example of the recognition for zebra to illustrate this issue. First, we have some known symbols for horses, donkeys, tigers, leopards, pandas, and penguins. Same as the supervised classification process, we use a convolutional neural network to extract visual features. Well, we also have the attribute descriptions of the object. For example, horses and donkeys have the similar shape, we call it horse-like. Tigers and leopards both have stripes. Pandas and penguins are black and white. Then, the model tries to recognize the horse-like animal with white and black stripes. In this way, the novel class zebra can be recognized. Formally, we have XTR for the subclasses visual features, YTR for the subclasses labels, and XTE for unsubclasses visual features, and YTE for the unsub labels. The object is to find a function from X side to Y prime side, where the Y side and Y prime side is disjoint. The knowledge transfer is implemented by compatibility function in common semantic space. Semantic information usually have two forms, attribute and word vectors. The attributes are annotated by human experts. For example, the AWA dataset in this figure have some attributes about color and shape. Another one is word vectors extracted from large-scale corpus by word2vect, Gov, and other NLP tools. One of the most popular methods is to learn a compatibility function between image embedding and semantic embedding using subclasses symbols. We also called it discriminative approaches. But the weakness of this method is that F is only trained by subclasses, which leads to a weak generalization ability of the model during testing. Some generation methods propose to generate features for unsubclasses to transfer the zero-shot classification into supervised classification. These models use GAN-based structures such as condition GAN to generate some samples from semantic embedding and random noises. Given the semantic information of unsubclasses, the visual features are generated. The generated features are then merged into the origin subclass features to form a complete visual embedding. However, both methods have some limitations. As you see, the discriminative approaches DEM and RNet achieves high accuracy on subclasses and poor performance on unsubclasses. These approaches tend to classify unsubclasses into subclasses. Although generative methods improve the performance for you, they sacrifice the accuracy of subclasses. So, to improve the quality of the generated features, we propose a novel attentive semantic preservation network to encode more discriminative as well as semantic-related information into the generated features with the category self-attention queues. The feature generation and the semantic inference modules are formulated into a unified process to promote each other, which can effectively align the cross-modality semantic relation. The category attentive strategy encourages model to focus more on intrinsic information of the noise-generated features to alleviate the confusion of the generated features. Specifically, the semantic preservation network generates visual features from semantics via autoencoder and reconstructed the visual and semantic features to preserve the bidirectional consistency. The category's attentive network calculates the class attention between each class to refine the generated features. The prototype-based classification network performs classification at semantic level. For semantic preservation network, the pseudo features x height is supervised with real features x parameterized by seat, where eSeat is the encoder. Similarly, the LS is a supervision of semantics. Then we remap the generated features to semantic space to keep the visual semantic cross-model consistency. With the LPRE, the feature generation and semantic inference procedures are formed as a more powerful unified constraint to encourage the clustering of the generated features from the same class, while preserving distribution and semantic-related information. As the visual and class semantic features are high-level representations, they are too normal, it's hard to capture sufficient information. So, we adopt adversarial learning for the visual semantic pairs. The discriminator is designed to distinguish whether the input is from the output of the generator or the real data distribution. Since the goal of ZSL and GZSL is to identify novel classes, the quality and generalization ability of generated features should be focused. We introduce the classification branch from the perspective of a prototype to reduce model complexity and make full use of non-semantic information. Besides, the answer classes semantic prototypes are also taken into consideration. The send-to-answer bias issue thus is mitigated obviously. However, it's no doubt that the feature confusion does exist in traditional and generalized ZSL learning. We introduce a category attentive semantic network to get the generator to generate more discriminative and higher quality visual features, where the ith row and jth column of key reflects the influence to which the jth class attends to the I class. The product between different generated features is regarded as a category correlation matrix. So each row of W after softmax represents a mode of attention, and alpha is a parameter to control the influence of attention for final generated features based on the consideration of generated features quality and interval stability. Then we can learn better features through attention, and it helps to refine the category features, enabling the similar images to have smaller distance, and the dissimilar images have larger distance. We conduct impairments on two coarse-grained datasets and two fine-grained datasets. Animals with attributes 1 and 2 consist of 50 animal species with 85-dimensional attributes provided for each class. Kotak birds and Oxford flowers are fine-grained datasets with 200 classes birds and 102 classes flowers, respectively. This table shows the performance comparisons for both traditional ZSL marked by blue box, and generalized ZSL marked by red box. In terms of average per class top 1 accuracy T, unsigned accuracy U, signed accuracy S, and their harmonic mean H. In traditional ZSL, the test set only comes from unsigned classes. It can be observed that our model achieves the best performance on 4 datasets against the previous state-of-the-art. Compared with the previous method, our model has a more average and robust performance on each dataset. It should be noted that our approaches achieves excellent results on 2 challenging fine-grained datasets, COB and FLO. This indicates that the effectiveness of the proposed method on handling the class confusion. For GZSL, we can see that our approach achieves superior and stable results on most datasets on the generalized setting, especially on U and H metric. The discriminative approaches such as late M and ZSL achieve high accuracy on S and extremely low accuracy on U, which is not feasible for the real application. Our ASPN achieves balance between the signed and unsigned accuracy benefited from the higher quality generative features. On the AWA2 dataset, our model is still very competitive, different from the best result of FV-GAN D2. Our ASPN improves the accuracy of signed classes as much as possible without sacrificing the accuracy of signed classes. Show the ablation study in this figure. The proposed SPN module outperforms the baseline across all these datasets in terms of unsigned accuracy, especially on COB with the highest 11.1% improvement. Besides, ASPN further improves the performance of unsigned classes while maintaining the accuracy of signed classes. More intuitively, we show the confusion metric comparison for popular class CW-GAN and ASPN. Class CW-GAN tends to recognize seal as virus in figure C, while ASPN can accurately distinguish these visually similar animals with the help of category attention. The same phenomenon appears in the classification of bat and rat, giraffe and horses, which further proves the effectiveness of the proposed method. In addition, this table shows that the proposed prototype-based classification model is more efficient with a lower complexity and better performance than the method of training a classifier. Low runtime consumption is also more realistic in application scenarios. That's all. Thank you.